Alright, so we are going to be looking at the parent function booklet today. It's really just a set of notes that I would like you to put into your notebooks. This will come in handy in the future. So let's go ahead and talk about what a parent function is. So let's go ahead and talk about what a parent function is. It is an equation that is the most basic equation for a set of functions. So let's say we had linear functions. The most basic of the linear functions would be called the parent function. So there's a family of functions, and that family would be called linear, and its most basic equation is its parent. So let's go ahead and do the linear function first. So the first one we're going to do is linear. So in the center, we're going to write linear. So if you don't want to print out the sheets, you don't have to. You could just do this in your own notebook. So in the center, we're going to write linear, and the function is, we know what the full function's standard form is. That's y equals mx plus b. So mx plus b, we should be familiar with that. So the function here, y equals x, is the parent function. Y equals x. So if we wanted to rewrite it in this form, it would be y equals 1x plus 0. 1x plus 0. So that's our mx plus b form. So this is our function. We want to go ahead and make a table. So let's go ahead and pick a few numbers, -2, -1, 0, 1, and 2. I'm picking some basic numbers for x. We're going to plug them into the equation to see what y equals. Okay? So we plug -2 in for x, and we get y equals -2. Then we plug in -1 in for x. Y equals -1. We plug 0 in for x. When x is 0, y equals 0. And so on. So one of the big questions that I get is, where did these numbers come from? -2, -1, 0, 1, and 2 for x. And we made them up. We made them up, but we made them up strategically because we wanted to know what the x-intercept was, and we wanted to probably know what the y-intercept was as well. So we plugged in 0 for x, and then we wanted to see what was going on either side of 0. So when x is less than 0, and then when x is greater than 0, we wanted to see what was happening. So we've got a nice set of numbers here, so we're going to go ahead and graph them. So we've got -2 for x, -2 for y. We've got -1 for x, -1 for y. We've got 0, 0. We've got 1 for x and 1 for y. And you can see that no matter what number we choose for x, y will always be that number, and that is a line that crosses through 0, 0, and it's a diagonal line. It's a diagonal line. So there we go. One of the things that we might want to note is that this is a polynomial of degree 1. That's an odd degree. So this is an odd degree polynomial. It's going down on the left, it's going up on the right. So it's got that down on the left, up in the right. If we had instead done y equals negative x, we would have gotten this line where it's going up on the left and down as we go to the right. But that's just another function. That's not the parent. The parent function is this one here. Again, we can rewrite it in the form y equals mx plus b, which is something you can do for any linear function. If you cannot rewrite it in the form y equals mx plus b, it is not a function, or it is not a line. One or the other is true. So, there we go. This is the first one. So let's go ahead and jump over to quadratic, which would be also a polynomial. We're going to focus on polynomials for the most part. So we're going to go ahead and do the parent function of a quadratic. So make sure you write this down. You can pause the video anytime. And also, once we write the parent function, if you want to try the table on your own, you can pause the video and try the table and the graph on your own, and then pick up and see if you did it right. So, alright, let's go ahead and reset. So our next equation here is the quadratic. So the quadratic is an x squared function. Its general form can be written in the form y equals ax squared plus bx plus c. It has other forms, but this is called the standard form. If you wanted to, you could write down the other two forms that we know, which is vertex form that is y equals a x minus h quantity squared plus k, and the other one is factored form. There's not really a nice, I mean there is, but I just usually write it y equals ax plus b times cx plus d, where a, b, and c in this case are not the same a, b, and c as these. So there we go. We're going to focus on the standard form though. So if you don't want to write these two down, you don't have to. They're not necessary. The standard form is what we're interested in usually. So parent function though is a simple form of this equation. And if you could imagine, just like linear, we need to have x involved. In fact, we need an x squared. And y equals x squared is the parent function. And you can see how this could be written in the form y equals ax squared plus bx plus c. We could write it as y equals 1 x squared plus 0x plus 0. So that is the standard form. It is a function then, and it is the quadratic parent function. So again, we're going to pick some numbers that we could plug in for x. Would do the same numbers as I did before. There's nothing really weird going on here, so this should work out for us. We're going to do -2, -1, 0, 1, and 2, because we want to see what's happening at the 0. We're hoping to find the y-intercept and the x-intercepts here, but this should help. So, alright, we're going to plug -2 in. So if we plug -2 in, we're just looking at the first number here. If we plug -2 in for x, we get -2 squared. And this is something that throws some students off, but notice x is being squared. All of x is being squared. So -2 is being squared. This is different than if you plug this into the calculator. You'd get something completely different. This negative is not being squared, just the 2 is being squared. Here, the negative and the 2 are both being squared. So we definitely want to be careful there. So the parentheses is important. So -2 squared is really -2 times -2. And 2 negatives make a positive, and 2 squared is 4. So we get a 4. Okay. Now when we plug -1 in, we're going to do the same. -1 squared, so that's -1 times -1, which is +1. And then 0 squared is 0, 1 squared is 1, and 2 squared is 4. We could keep going, but these are good numbers for our small graph. So we could keep going, but this is definitely plenty. So -2, 1, 2, 3, 4. So we go left 2, up 4. We go left 1, up 1. 0, 0. Then we've got 1, 1. That's right 1, up 1. And then 2, 4. We go right 2, up 4. And if I graph this correctly, we should have a nice U-shaped graph, fairly U-shaped. If it's not, it's just because I didn't graph it very nicely. But so there's some big notes here. We're symmetric. We're symmetric. So the vertex is this lowest point, and everything on the right looks just like everything on the left. It's symmetric. It's like a mirror image across this vertical line that the lowest point is on. So symmetric about the vertex. So about the vertical line the vertex is on. This is always true. This is something to keep in mind that we could have if we had known that our vertex was 0, 0, which we can obviously see. But if we knew that just by looking at the equation, then we could have just done the right-hand side and then mirrored the left-hand side, not had to worry about doing 5 points. We just do 3. We would have gotten the other 2 for free, because 1, 1 and -1, 1 are symmetric about the vertical line that 0, 0 lives on. So that's kind of a time saver if you learn that. So if you could find the vertex right away, that can save you some time in finding points. What else is important to note? As we go to the left, we're going up. As we're going to the right, we're going up. So obviously, if this was y equals -x squared, we would have had a parabola that was going down. So we would have gotten a shape that looked like this. Going down. And 0, 0 still would have been our vertex, but we would have been going down. And so with an even function, which is what a quadratic is an even polynomial, we're either going up on both sides or down on both sides. So in this case, we're going up, up. So as we go to the left, we're going up. As we go to the right, we're also going up. So, and that's the general rule for even functions, even polynomials. We will go up both on the left and the right forever. And in odd functions, odd polynomials, we will go down on one side and up the other. So that's kind of neat. All right, let's go ahead and do a couple more. Hopefully this makes sense. Go ahead and write this down. Oh, I erased my word, graph. So go ahead and do a cubic. Alright, so we're doing the cubic next. I think I've cleaned it off appropriately. Alright, so a cubic function is raised to the power of 3. So we've got y equals our standard form, y equals ax cubed plus bx squared plus cx plus d. So that's our standard form of a cubic. Obviously the parent function is much simpler looking, and we could imagine that it is y equals x, because we always need an x in there to be a parent, and it is cubed. So y equals x cubed. We could rewrite it y equals 1x cubed plus 0x squared plus 0x plus 0. Alright, so we're going to go ahead and plug some numbers in to our table. I'm going to stick with my traditional -2, -1, 0, 1, and 2. Really, I want to show the pattern. So I'm seeing if there's a pattern here. So I'm going to go ahead and plug -2 in for x, -2 squared, cubed, -2 cubed. So that's -2 times -2 times -2. So we might want to write that out. -2 cubed is -2 times -2 times -2. This is a multiply on -2 times another -2. So we've got 3 negatives makes a negative. This is important to remember, is that an even number of negatives will make a positive. An odd number of negatives makes a negative. So we get a negative, and then 2 times 2 is 4, times 2 is 8. So we get -8. We plug 1 in, -1 in. -1 times -1 times -1. We don't have to write it out, but 3 negatives make a negative, and 1 times 1 times 1 is 1. So we get a -1. 0 cubed is still 0. 1 cubed is 1, and 2 cubed is 8. So there we go. Alright, so we want to graph these. It's getting more challenging to actually plot these on the graph, but that's okay, we'll get it. So go left 2, and we're going to go up, down 8. Left 2, down 8. And then we've got left 1, down 1. And we've got 0, 0. Then we've got right 1, up 1. And then we've got right 2, up 8. That's okay. It's a little bit up there, but that's okay. So this thing is tending to go down very steeply, and then it smooths out a bit, and then it's going up steeply. So as we go to the left, we're going down very steeply, and that doesn't mean that this is not going to the left still. It's going to the left forever, and down forever. As we go down, we are going to the left forever. As we're going up, we are going to the right forever. It's just that it takes a lot more up to go right a little bit. So again, we're going down on the left, and we're going up on the right. Again, if we had y equals -x cubed, it would be mirrored, so we would get something that looked like that. Whereas as we were going to the right, we'd be going down forever, and as we went to the left, we'd be going up forever. So it would just kind of be flipped. You can see if you reflected it across the y-axis, you'd get the negative shape. But you can see all odd polynomials go down on one side and up on the other. And let's go ahead and do one more to prove the evens go up, up, and or down, down. So let's go ahead and get this out of here. We're going to have a little bit more difficult time graphing decent points, but that's okay. We'll do our best. So let's go ahead and get this out of here. And we're going to do the quartic So we're going to do, this is our last polynomial, is the quartic. And I'm pretty sure I spelled that right. Quartic. It just needs 4. So this is a 4th degree polynomial. So it could be written in the form y equals ax to the 4th plus bx cubed plus cx squared plus dx plus e. Now quartic raised to the 4th power. So again, this is the parent function. It's the most basic of this set of functions. So this family, any function that's in the family can be written in this form, including the parent. So if we were to write it in the parent function form, we would write y equals 1x to the 4th plus 0x cubed plus 0x squared plus 0x plus 0. So there we go. All right, y equals x to the 4th. And we're going to go ahead and do the same set of numbers, -2, -1, 0, 1, and 2 with the quartic. And so -2 to the 4th, that's 2 times 2 times 2 times 2. Well, we already know that 2 cubed is 8, times 2 is 16, and 4 negatives make a positive, so it's positive 16. And then -1 to the 4th is 4 negatives, so it's a positive 1. 1 times 1 times 1 times 1. And then 0 times itself, total of 4 times is still 0. And then 1 to the 4th is 1. And 2 to the 4th is 2, 4, 8, 16. So 16. 2 to the 4th is 16. Alright, so we've got -2 comma 16. Well, we went up to 8 here, so 16's like way up here. Way up here. Okay? And then -1, 1. Kind of a pattern here. 0, 0, 1, 1, and then 2, 16. Way up here. So way up there. Way up there. Okay. So again, it looks like a parabola. That's because we don't have the cubes and the squares and all that stuff that kind of mess things up. So generally, the form of a 4th power quartic will often look like this, where we have up to 1, 2, 3, 4 zeros, up to 4 zeros. So you can look at the number, the exponent, and that tells you how many possible zeros we can have. In this case, we only had 1 0, and that was at 0, 0, so only one real root. But here, if we had a graph that looked like this, we would have 4 real roots. So that happens. All right. So that's our parent function. The main thing that I want us to note is that, yes, it is going up on the left and up on the right. So as we go to the left, we're going up. As we go to the right, we're going up. And again, if we had y equals -x to the 4th, it would be going down on both sides of the parabola. But again, it could have this appearance over here. So I mean, this is definitely possible, but it could look like this. So look again, up to 4 real zeros. All right, so let's go ahead and do one last one that I think is important. There's obviously tons and tons of functions, but we're going to look at each of these other functions as we get to them. But I do want to throw one more in. So we're going to go ahead and try the rational function here next. So this is kind of the logical progression that we are moving towards, is the rational functions. Once you understand polynomial functions, and I think we're getting close to understanding them. We're not quite there yet, but we are moving towards the rational functions as our next focus. So let's go ahead and look at a rational parent function. So that is y equals, and in the notes, a rational function is y equals a polynomial divided by a polynomial is generally a rational function. And in fact, the polynomial functions are rational functions. If you think about the parent function of a line, y equals x, that is a rational function, because it is really y equals x divided by 1. X is a polynomial, and so is 1. 1 is a polynomial. So we've been doing rational functions. We've just been doing ones where the polynomial in the denominator is just 1. So any polynomial divided by another polynomial, then we've got ourselves a rational function. So we've been doing them. We're just going to do ones that are a little bit weird. So the parent function is when you have 1 divided by x, 1 over x. So this is our parent function, y equals 1 over x. So we're going to go ahead and plug some numbers in. So we get negative 2, negative 1, 0, 1, and 2. Unfortunately, we may not be able to plot all of these points, but we're going to plot the ones we can. So let's go ahead. And we may have to add some more points in, which I didn't make this very long, so we may need to do an additional t-chart and add some more points if we don't have enough going on here. So we've got our y, which is important. We've got our x, which is also important. Alright, so 1 divided by x, we're going to plug negative 2 in, so we get y equals 1 over negative 2, and that is negative. We can move the negative to the numerator for free and get negative 1 half. Negative 1 half. That's a good number. We can graph that. It may not look good to you, but it's a good number. Okay, we're going to go ahead and plug negative 1 in. We get 1 divided by negative 1. We're plugging negative 1 in for x. We're replacing x with negative 1. 1 over negative 1 is negative 1. 1 divided by 1 is 1, and you get a negative. Plug 0 in. 1 divided by 0. 1 divided by 0 we've gone over before, I'm sure, in geometry. I think we came across it a few times. Hopefully you've gone over it enough times where you know that anything divided by 0 is undefined. Undefined. Okay? So I'm just saying UND, short for undefined. Alright, 1 divided by 1 is 1, and then 1 divided by 2 is 1 half. Let's go ahead and plot these points and see. I don't think that's enough information though. Negative 2, negative 1 half, negative 1, negative 1, then we've got 1, 1, and we've got 2, 1 half. So let's go ahead and plug in for x, 1 half, and negative 1 half. Remember, 0, 0 does not work. 1 divided by 0 does not work. So we can't really see how to connect these two. And that's because they don't connect. They diverge. They're not converging. They're not getting closer to each other. They're actually getting further away. As we move towards the 0, 0, as we move towards the y-intercept, I should say, y-axis, we're actually, it looks like they might be, this one's going down, this one's going up maybe, right? This one looks like it's going up, this one looks like it's going down. They're going away from each other, so they're diverging, not converging. Converging, they'd be getting closer to each other. Looks like they might be getting further away. So let's go ahead and plug 1 half in and see if this is true. 1 divided by 1 half, so y equals 1 divided by 1/2. Well, 1 could be rewritten as a fraction, 1 over 1 divided by 1/2. We've got a fraction divided by a fraction, which we've learned many years ago probably, that a fraction divided by a fraction is the top fraction times the reciprocal of the bottom fraction. And multiply across, 1 times 2 is 2, 1 times 1 is 1, we get 2 over 1. So multiply the 1 times the 2, we get 2, 1 times 1 is 1, and 2 over 1 is 2. Again, if we do the negative, we're just ending up with a negative sign. Oops, not there though. And we end up with a negative 2. So that's when we plug negative 1/2. So there we go. All that fun work. And what we end up with is 1/2 comma 2, that's this one, and negative 1/2 negative 2. So if we were to graph this, and if we were to pick a lot more points, this is what shape we're getting. So there are what are called asymptotes happening here. We technically have ourselves a vertical asymptote on the y-axis and a horizontal asymptote at the x-axis. These two functions, or these two graph pieces, never touch, and they cannot cross what are called the asymptotes. Never cross. You may not cross an asymptote. So this line is getting closer and closer to 0, or to the y-axis, but it's never going to touch it or cross it. And as it goes up and to the left, it's getting closer and closer to the x-axis, but it's never going to touch it, ever. And same with the right-hand side. We're getting closer and closer to the y-axis as we go up, but we never touch it. And as we go to the right, we're getting closer and closer to the x-axis, but we never touch it. So this is logically where we're going, is to the rationals. So I wanted us to see that. You probably graphed these years ago, but it's probably been a while. So, all right, I think that's it for the parent function book for now. We will add more in the future. So when we get to like sine, cosine, and tangent, we'll go ahead and do the parent functions of those. And when we get to exponentials and radical functions, then we'll go ahead and add those in. These are basically notes, and when you turn this in, you're basically turning in notes, but it is worth an assignment. So make sure you submit your parent function booklet. It could be that you wrote it in your notebook, and that's fine, or that you printed out the sheets, either one, whichever one you feel more comfortable with. And so hopefully this makes sense. And that's it. All right. Have a wonderful day.